All right, so I'll start the recording. And right now I will go through a quick run through of homework 4. So let me just share the screen. And so what we just talked about before the recording started is that people are having an issue on maybe just on Windows or having an issue with trad plots, asking them to rebuild Meshcat, and then that's not quite working. So there's a few different things that I could do to fix this. I will do one of them today, and I will update both the repo and make a Piazza post where I talk about like how to fix it basically and just give you the updated fixed version. Sorry about that. I know it's always frustrating when you have the build issues. All right, so this homework, the idea is to be relatively simple because you guys are working on a bunch of project stuff right now, ideally. And I know like things get kind of crazy at the end of the semester. So these are just kind of two easy-ish questions based on the stuff that Zach's gone over recently. So the first is going to be on iterative learning control, which if you remember, Zach is like, in his eyes, this is like the sample efficient alternative to modern RL or maybe deep RL specifically. And what we're doing it for is just on a car. As it does something called a moose test. So I'm not sure how well this video will show, but basically it's like this classic thing where the car has to like swerve to avoid what is ostensibly like a moose on the road. And it's pretty funny. If you watch a bunch of old videos, like all the old cars did horribly on this, like really, really terribly. And there's been like recently in the last few years, there's been like a bunch of new cars, like large SUVs that like can't really do this. So it's a weird like auto test. And I thought it'd be a cool thing to do ILC on because like obviously this relies on a lot of individual problem parameters that are like kind of hard to estimate. But this is like a very repeatable maneuver. So it kind of fits really well in the ILC framework where like I run a sample, I get a result, I update the feed forward control, and I keep doing that over and over again until I converge. So here are the state and control. So we have X and Y. These are like we're looking at just a 2D bicycle model. So what's pretty common for autonomous vehicles is that we'll just think about things in terms of a dynamic bicycle model. So there's like a kinematic bicycle model. This is the dynamic bicycle model. So what we have is we have a 2D position, PX, PY. We have an orientation, theta. And then this delta, this is our steering angle. V is our velocity, and omega is the same as the derivative of theta. So it's just our angular velocity in this 2D plane. And then our controls are the controls that you'd have in a car. So the first one is A, which is our acceleration. So basically like putting your foot on the gas. And we just assume that like gas and brake, the gas is just like a positive A, the brake is just a negative A. And then we have delta dot. This is the derivative of our steering angle. So this will be me like speeding up or slowing down how I'm turning the wheel. And the reason we do this is because we kind of want like some element of smoothness in our controls. And so oftentimes people will not do this. They'll get really wacky controls. So what's super common is people have the velocity as a control, which lets you go from time step to time step. You go from like, 10 meters per second to like a negative 3 meters per second, which is obviously not how cars work. And the same is true with the steering angle. Like, you can move it very quickly, but in reality, it's always going to take some time to get from one steering angle to another. So just if you add these controls as the derivatives of the velocity, so A, and the derivatives of the steering angle, so this right here, what we get like some element of smoothness in our controls that is just much more realistic because at the end of the day, we're trying to use this simple bicycle model to approximate a much more complex model of a car. And this allows us to do that with like not, straying too far from what a car would do. So here are the dynamics, relatively simple. There's also, you should know if you are kind of reading stuff about like the nonlinear bicycle model, you'll find there's kind of 3 different model descriptions and it's based on where they consider like the frame of reference inside the car. So I chose to do everything with a center of gravity, but there are 2 other alternatives. One is about like the front axle and the rear axle. So just know if you ever see like a model in the wild and it looks like a little different, it's probably because it's using something else as for the reference. Here's RK4. What we're going to do is we're going to load a car trajectory. So what I've done is I've solved, an optimal control problem offline with an approximate model that makes this car do the moose test. And the idea is that like, we're going to use this approximate model as like a starting point. And in reality, because the true car dynamics are different. So here we see the true car dynamics, we have like a slightly different model. So we have different kind of lengths of the car itself. And then we also have these like sluggish controls, which is just like kind of just some added nonlinearity and inaccuracies into the real dynamics, such that we need a controller to account for them. And the idea is that when I take this trajectory that I solved for offline and I run it on the true car dynamics, what I get is this thing does not do the right swerve whatsoever. If you think about this, this is like, there's a lot of control happening that gets me from here to here and then back to the middle. And if at any point I do these incorrectly, then there's no way I'm going to get back to pointing directly straight. I'll end up like pointing in some weird direction. So the idea is that like I take this trajectory offline, I run it on the true car dynamics, and I get a crazy result. So our solution is that we're going to use iterative learning control, and we're going to do this on a few samples, and we're going to do this rollout. We're going to solve the ILC problem, do another rollout, and we're going to keep doing this until we actually get like a good looking trajectory. And we'll see that this actually works even though we're using like wildly approximate Jacobians and everything. And so this first thing is just like kind of sim to real gap. This is just kind of making the point that I just made, that if I take these controls that I got offline and if I simulate them, so you'll add your simulation right here. If I simulate them, I'm not going to get like a good looking result. And my X sim, this is my like simulated trajectory on the real dynamics, is not going to look like my X ref, which is what my offline thing thinks it's supposed to look like. All right, so next we have the so what we're doing in ILC is that we do a rollout, and then we're going to solve a convex control problem for an updated feed forward control. And then we're going to update our U with what we got from the convex problem. So this is the exact same from, I'll make a point here because the notation is like super important. And a lot of the issues you guys will have are going to come from this. So I try to stick with the exact notation Zach did, but like this is truly it for ILC. So let's take a note of everything. So we have X naught. This doesn't change ever, right? We always assume we have the same initial condition. And then we have U bar. And this is very important. U bar, this is what we're trying to solve for. So ILC is using all this stuff to update U bar. And this is our feed forward control that we give to the system. So we do a simulation, we do a rollout. This gives us like our XM and our U bar. So in the case that we're just doing feed forward control, U bar that goes into the rollout is the same as U that comes out. If I had a closed loop controller, my simulated U would be a little different because I'd have like the, U feed forward minus K times X minus X ref. So if I had a feedback controller inside the rollout, which we don't have in this case, we're just doing feed forward control right now. But if I had that, I would have a different rollout U than I do for my U bar. So, but because we're not doing that, because we're just doing a feed forward rollout, this U bar is the same as the U that comes out of here. And then what we do is that we solve a big QP where we have our cost function. And this is a function of the wherever we linearized about. So likely this is the offline X ref, U ref. And then we have these deltas, and we're solving for the deltas. And then we're solving for a linearized version of the dynamics model. And so if you remember, I made a point in previous recitations that this whole delta X equals A delta X plus B delta U. This model really only applies if the system has been linearized about a dynamically feasible trajectory. And so if you imagine right here, like the whole thing with ILC is that we're kind of like hand waving, assuming that like these A's and B's are close enough to the real Jacobians that we just accept that. And there's no dynamics residual. So there's no dynamic infeasibility because we assume that this X and U, we just ran it on the real system. So there's no dynamic infeasibility there because we ran it on the real system. So this X and U, they follow the real dynamics. And this is what allows us to use the delta X equals A delta X plus B delta U without any dynamics residual in that Taylor series. And so what we do is that we solve this QP, we get delta X delta U, and then again, we're innovating upon the U bar. So U bar equals just U bar plus delta U. So this is super important. It's a little easier in this case because there's no feedback control inside this rollout function. We're just doing feed forward. But the U that we're updating is U bar. And we are only forming these Jacobians, A and B. We're forming them once. So we form these A and Bs offline. We take our approximate model, we take our initial XREF, UREF, and we form these Jacobians once. And then ILC does not form new Jacobians. So the idea is that we're reusing the same Jacobians for each of these solves. All we're doing is we're updating the gradients. So if Zach did this where he wrote out like the KKT conditions, and we just assume that our cost Hessian and our constraint Jacobians in that KKT system are the same for every iteration. And we're updating their right-hand side, which if you remember is the gradient of the cost. And on the bottom, we have the constraint violation. And again, the constraint violation is 0 because we assume this rollout came from the real system. So, this is dynamically feasible. There is no constraint residual here. And then we'll do this until we reach some sort of tolerance. So here's our specific cost function. So we're trying to minimize X and U, and we're using this XREF UREF. This comes from load car trajectory. So this XREF UREF, this is what we're trying to track. Like we're doing our best to track this. Here's our cost function. So it's a function of X and U. And then what we do is that, ILC, we form these Jacobians once. So what we're doing is that before we start the ILC loop, just when we're given XREF and UREF in our approximate dynamics model, we form this A and B for each time step. And we do this with our approximate dynamics model about XREF UREF. And again, I know I keep saying this, but it's very important. This happens once before the ILC loop. And here's just FXU is our approximate discrete dynamics. So this is, estimated car dynamics in RK4. And then just to like clarify some of the notation, XREF in code is just XREF, UREF, UREF, XM, XM, UBAR, UBAR. And then what we do is that when we solve the ILC problem, and this is where, like, again, notation is super important. When we solve the ILC problem, like we're solving for delta X, delta U, and then our cost function is just this function up here. But opposed to taking just X and U, I'm now taking XM plus delta X and U bar plus delta U. Because I'm assuming that like my A's and B's are approximately going to represent if I were to linearize about the rollout trajectory, which if you remember is XSIM and U bar. And that's because U bar is our feed forward control. So U bar is the same as our U sim. And what we're going to do is that we're going to initialize U bar with UREF. So remember in the previous section up here, we showed that if we run UREF on the system, we get a trajectory that looks nothing like XREF. So our UREF is like not the right answer whatsoever. But what we want is that like we need to start this with something. So we're going to initialize with UREF. It won't be good at first, but this is like how we're going to initialize U bar. So initialize U bar with UREF. And then we're just going to update U bar equals U bar plus delta U at each iteration. And it should take 5 to 10 iterations to converge. And our convergence criteria is going to be when delta U dips below 1E minus 2. And a nice thing here is that this problem is set up in a way such that we don't need any sort of line search. In general, I guess this would be a kind of a fun experiment on hardware, is that you could implement a line search where like every single new step length, I do a new simulation. That's how you would do a line search in this scenario. For this specific example, we don't need to use a line search though. All right, so I gave you some functions as usual. You can use them or not use them. It's up to you guys. I feel it's a little clearer to use these. So one is, here's our cost of our trajectory. So XSIM and U bar, these are the rollout states. So XSIM is our true trajectory. U bar, this is the controls that we're working on. XREF and UREF, this is just the same constant things that we got from our offline trajectory. And then QR, QF, this is the LQR tracking cost. Is trying to track XREF, UREF. Here's a utility that will convert a vector format. It's going to take a 2D array and convert it into a vector of vectors. So, when we solve this with context.jl, when we did this in the last homework, but we solve things as 2D arrays. And then just in general, when we're working with trajectories, we like treating things as vectors of vectors. So this is just that same utility you had in the previous 2 homeworks, where I'm just converting back and forth. And then this ILC update, give you some skeleton code here. So XMU bar, these are the actual simulated states and controls on the real system. XREF, UREF, this is the offline stuff. A's and B's, these are the Jacobians that, again, we calculate once before we start ILC. And then QR, QF, these are our LQR tracking cost terms. And then here's just some skeleton code for how you'd solve this problem with convex.jl. All right, and then this next thing, this is actually like where we put in ILC. So go ahead and look at the to-dos. So here's our tracking cost. Here's our model, which is like slightly wrong intentionally. And then we have everything that we need in our params. Feel free to add things to params if you have to, if you're doing other stuff or whatever. And then XSIM, again, this is going to hold the trajectories with the real dynamics. Then U bar, this is the feed forward control that we're working on. We're going to initialize this as UREF. So we're just initializing our ILC solver with UREF as our initial guess. And then we're going to calculate our Jacobians, which, remember, happens once, happens offline, does not happen inside the loop. Here's some logging stuff that just gives you some nice outputs to see what's going on. And then, we look back at this lecture, we got a rollout, a solve, and an update. So we're doing rollout, check the objective value, solve the problem, ILC update, and then update the controls, and then we'll just log to get an idea of what's going on. All right, so that's question 1 for ILC. Do we have any questions on maybe things that are in the assignment that I didn't quite cover, at least for this question? If not, I'll go ahead and move to question 2 now. All right, so this question is like super fun. In past years, it was like a little, honestly, it was terrible. So it was like very hard in previous years. I did my best to try and make it like as simple and clear as possible, because I think it is like a relatively simple idea, but just like the nature of having a pre-planned contact sequence in hybrid trad-hop is just always going to be a little messy. So the idea is that we have this very simple walker where I have just 3 rigid bodies. I have the center, the gray thing, and I have these 2 legs, and then I have like prismatic joints between each foot in the center body. So like kind of like a foot, I can like push and pull these things, and then I can like exert a torque and I can move the 2 legs. And the idea is that like, how can I use these controls to make this thing that is unstable, how can I make it like actually walk nicely? And so what we do is that we'll talk about the state. And so there's a lot of notation here, but it's all like written out explicitly. So the idea is that we have, remember, we have 3 just spheres. So 3 rigid bodies. What we have is that we have a position and a velocity for each rigid body as expressed in the world frame. So RB, this is our center body. This is the gray thing. RB has a position X and Y, and then a velocity X and Y. And then we have foot 1 and foot 2. Both these have their own positions and velocities. And our state is just the concatenation of all these things. So we have, here's the position of the body, position of foot 1, position of foot 2, velocity of body, velocity of foot 1, velocity of foot 2. And then our controls, F1, this is the prismatic joint between the body and the first foot. F2 is the same for the second foot. And then torque, or tau, this is the torque that we can exert that kind of like swivels the legs, if you will. And then, PXB, this is the X position of body. This is the Y velocity of foot I. These are just examples that goes more of like what this notation is. So I know there's like a lot of like, looks like there's a lot going on here. Just if you take a second look at it, it's really not that crazy. All right, and so what we're going to do is that if we think about this walker, we have multiple different configurations that would change the dynamics. So if I'm just like a walker floating in space, I have one dynamics. If I have like my 1 foot pinned to the ground, I have another set of dynamics, or the left foot, another set. So the idea is that we have different dynamics based on the configuration of our robot. And the whole point of hybrid trad-hop is that we're going to pre-specify exactly when these things are happening in terms of which time steps, and then just solve a normal trad-hop problem. So nothing crazy. This is the same style of just, nonlinear trad-hop problem that we've solved all semester. But now what we're doing is that we're having different dynamics at every time step based on where we are in this contact sequence. So the first thing, this is stance 1 dynamics. And so these are the continuous time dynamics when foot 1 is in contact with the ground. So let's look back up this animation real quick. So if this were going really slowly, we see that we have like 1 foot, other foot, 1 foot, other foot. In each of those regimes, we're going to have a different set of dynamics. So like I said, stance 1 dynamics, these are the continuous time stuff when foot 1's in contact with the ground. Dynamics, or stance 2 dynamics, this is just when the foot 2 is in contact with the ground. And then here we have these jump maps. So if you remember, Zach talked about this in class, we have, foot 1 experiences inelastic collision. So this is like the foot hitting the ground. Jump 2 map, this is the foot 2 hitting the ground. And then we'll just use normal RK4 to turn these things into discrete things. So now is where like the indexing kind of comes in. So like I said, we have a trad-hop problem. In this case, we have 45 time steps. And what we're doing is that we're going to dictate to you, and we're going to pre-prescribe the contact sequence. And what that means is that of those 45 time steps, we're going to tell you exactly which dynamics apply at which time step. So here we see that stance 1 applies from time steps 1 through 5, and stance 2, time steps 6 through 10. So we have a different set of dynamics for these contact sequences at the time steps. And then also we have these jump maps. And don't get like too confused by this notation, but this is you'll see set subtraction, this like right backslash right here. What this means is we have this jump map that's going to take us, if we're transitioning from mode 1 to mode 2, I use our jump 1 map. And if I'm transitioning from mode 2 to mode 1, I use my jump 2 map. And all this says is that like these sets is going to be, so like 5, 15, 25, 35. It's the last time step in each of these things. 15, 25, 35. And then the 45 is the last one, so we don't have to worry about that. And then 10, 20, 30, 40. This is the last in this one, and this one. And the reason we're doing this is because we want to specify these jump map sets, because this is when the jump map applies going between each of the two modes. And then what we'll do is that I think this is like a much easier way to do this is that we'll just store these sets. So here's how I compute them. This is just, I'm using list comprehension and just vcatting it to produce a big vector of all these indices. And I'm just showing you how I can take an integer like 5. I can determine if 5 is in M1, if 5 is in J1, or if 5 is in M1 and not in J1. So this is like, 5. The set notation version of this is 5 within M, but M1, but not within J1. So I just think using this kind of like set membership notation is going to make this problem like much easier to do. So now we have the full traject problem, which, like everything in this class, looks crazy at first, but it's truly not that crazy. So the first thing we have is that we have an LQR cost function that we love this. We use it all semester. And all we're doing here is that we're trying to take an XREF and a UREF that we compute, and we're trying to track it with our trajectory X and U. So this you've seen 1,000 times, nothing crazy. Now we have the problem itself. So our cost function J, this is what we have just up here. We have an initial condition, we have a terminal condition, and then now these 4 blocks, these are our dynamics. So remember, every single time step, we're deciding a priori. So like before we start the problem, we're pre-prescribing exactly which of these time steps certain dynamics will take place. So if the time step K is in M1, but not in J1, then we just use the discretized version of stance 1 dynamics. If the time step K is within M2, but not J2, then we're using the RK4 in stance 2 dynamics. And then if K is in J1 or K is in J2, we're going to use the jump map attached to those discrete dynamics. So a really important thing to know here, amongst these 4 dynamics constraints, there's only ever one set of dynamics for every time step. So these conditions right here, these guarantee that we're only using one set of dynamics at every time step. And then we have some constraints here that says that, if K is in M1, so remember that when we wrote down these, like what it was to be in stance 1 to stance 2, it's like foot 1's pinned to the ground, foot 2's pinned to the ground. So all we're doing is we're saying at those time steps, so if K is M1, then that foot 1 must be pinned to the ground. So 4 and 6, if you look up at our state, these are the Y positions of foot 1 and foot 2. It just says that like if I'm in stance 1 implies that the foot 1 has to be pinned to the ground. I'm just saying like make sure that Y is actually pinned to the ground. And now this constraint is a little more interesting. This is a length constraint. So what we're saying is that like if I am extending these prismatic joints, I have a certain range I can do that, right? I can only like pull the joints in a certain amount. I can only push them out a certain amount. And the idea is that the norm between the positions of the body and each foot must be between 0.5 and 1.5. So that just means that if you look here, we'll see again that the legs are kind of lengthening and shortening as they go, right? And so what we're doing is that we're basically constraining this such that the legs can only lengthen a certain amount and they can only like shorten to a certain amount. And then the last constraint just says that these are all the Y positions. So all the Y positions of all 3 rigid bodies, so the body and each foot, should always be greater than or equal to 0. And so what I've done is I've gone through and like kind of written out like what these constraints are. And if you remember, we do things in IPOpt. We used this form to write down our problem. So we have a cost function, we have an equality constraint function, an inequality constraint function, and then primal bound constraints. So this is the exact same as we did in our previous homework. We're using the same function, this fmin_con. So it's the same interface to IPOpt that we used before. And now what we're doing is I'm just going to tell you where these constraints go, because there's like, with the inequalities, there's ways you could do it that make more or less sense. So all of these are equality constraints. So nothing crazy, just see these are all equality. And then these 2 right here, these are going to go in our inequality constraint function. So inequality, inequality. And then this last constraint, this is just a bound on our primal variables. So remember, X is one of our primal variables. We're solving for it. So I don't have to write an inequality constraint for this. I just have to change the primal bounds, which is this right here. So ZL, ZU. I just change the primal bounds such that the lower bound is 0. And that would just guarantee that those Y, and this is just for the Y positions of each rigid body. So that's how you handle this constraint. And then here's just another clarification of what these F1 and G1 actually mean. So F1 is the discretized version of our stance 1 dynamics. F2 is the discretized version of our stance 2 dynamics. And then jump map 1 and jump map 2 are G1 and G2. So in the constraint, when you see something like G2 of F1 XK UK, this is really just jump to map of RK4 of stance 1 dynamics. All right, so here is a reference. This is just, I wrote this out for you because in previous years, this was like people were generating slightly different references, which was like causing tests to fail. So now I'm just giving you the reference. I'm just saying that we're going to have like, assume all 3 rigid bodies are just like sliding, like linearly interpolating from one spot to the next spot. Like not that sophisticated, but like we just want this thing to move, and that's how we're getting it to move. And so this is the exact same as questions 1 and potentially question 3 on homework 3, depending on how you solve question 3. But we're going to stack up our Z into, or sorry, stack up all of our X's and U's into a big Z vector. And we're going to solve with F-min-con using this interface. And the idea is that the thing you solve for, it should look just like walker.gif. So that's this right here. It should look exactly like this. Like in this case, based on how we're initializing, this is kind of like the only local minima that IPOP will ever go into. So if it doesn't look like this, you have a mistake somewhere. And so just like homework 3, I had this create IDX function. And this is just a convenience thing that you should probably use. And this just tells us the indices of how I can take this big Z vector and how I can pull out individual X's and U's. Also some constraint stuff. And what I'll do is I'll post, and once everyone turns in homework 3, because there's a few people using late days, I'll go ahead and I'll post up the solutions to homework 3. And you guys can see like, I guess my take on an easy way to do something like this that'll like kind of demonstrate how we use this IDX stuff. But a lot of you probably already figured it out. Here's our Walker cost. And again, you can use or not use any of these things. This is just like, this already fits in the framework, already fits in the API. So like, it just makes most sense to add this to here. But if for whatever reason, you can't stand this in the way it's set up, like by all means, you can do whatever you want to. Pull out all these relevant things from params, input the cost, which is just our LQR cost function, that J. And then here we have the dynamic constraints. And so basically the way this is like, most of the work in the problem is going to be figuring out how to write down the mathematical optimization problem that we just showed for a specific, like how do we put it in this F-min-con frame. And so basically what we're going to do is we're going to iterate from k equals 1 to n minus 1. And at every time step, we're just going to figure out which dynamics we're using. And so this is like, we'd use the logic that we talked about up here. So we use this logic. This is how we do kind of set membership in Julia. And we'll use this based on K to figure out which of these 4 categories we want our dynamics constraint to actually be in. And then we're going to have the stance constraint. So this is that the values of X4 and X6 based on which stance mode you're in are actually going to be like Y values equal to 0. So that is, and I wrote down the numbers of everything inside the constraints. This is not our 7 and 8, constraint 7 and 8. So foot 1's pinned to the ground, foot 2's pinned to the ground. This is a stance constraint. Then we have our Walker equality constraint. This is just where I just stack everything up. So this should be of this length 2nx, n minus 1 nx plus n. And this is because we have initial condition constraint, length nx, terminal constraint, length nx, dynamics constraint, which is I gave you a function for up here, and then stance constraint, which I gave you a function for right here. And so the idea is I just stack all these things up and return them. And now we have the Walker inequality constraint. So if we look back up, the only inequality constraint that we have here is that length constraint between the rigid bodies. So that distance must be between 0.5 and 1.5. And there should be 2 n constraints here because at every time step, there's 2 of these distances that we're constraining. And it's important to note that with IPOP, remember when we write the inequality constraint, it's always between a CL and CU. So for our inequality constraint, we have a lower bound and an upper bound. And so what we're doing is we're saying like, When I write down this constraint, I know the lower bound is 0.5 and the upper bound is 1.5 for this length constraint. So basically just use that to write down this constraint. Don't like double up your constraints. Like if you had to write this as far as everything less than or equal to 0, you'd have to double up these constraints because we have a lower and an upper bound. But because the API for fmin_con and IPOpt lets us specify those ranges, we'll just use that instead. And then here we go, dynamics parameters, problem size, initial and goal states. Here are the index sets M1, M2, J1, J2. Here's our reference. Here's our cost function. We're going to create IDX, and then we'll put everything useful that we'll need into params just so we can access it. This is, again, the same as homework 3, just so we can access this in fmin_con. And then we have some primal bounds that you got to update. We got some inequality constraint bounds you got to update. And then you should really, it's smart to initialize Z0 with xref, uref. This is like a really great initial guess for how this looks. And then it's always like kind of safe to add a little bit of noise to it, because sometimes there's some weird Jacobians that like you can't quite compute if everything's 0 for whatever reason. So always adding a little bit of noise is smart for any initial guess. And then remember, if you're having forward diff issues, so the most common one is no method matching for float 64 of big forward diff input. If you see that issue, this is what we went over in homework 0. If for whatever reason you can't figure out the forward diff error, you should look at homework 0 though if you want to remember how to do it. If this doesn't work though, you can always just change this to finite. And this will compute a finite difference derivative, which is less accurate and slower, but it doesn't have any of the same forward diff bugs. Not bugs. It doesn't have any of the forward diff requirements of how your code has to create memory. But in general, you should try and use auto diffing. And then here's our fmin_con call, nothing crazy. Then we just pull out our x's and our u's using our IDX and then plot everything. And the testing is, should be pretty self-explanatory. All right, so I think that's a pretty solid run through of Q1 and Q2. Any questions on either this question or just the homework in general?
Yeah, I have one question. So I was curious if you could sort of give an overview, like what would be the process to make the reference trajectory a little bit more robust. Like, I mean, this is very particularly like fine-tuned, it seems like you worked on. And I'm trying to understand like what this process would look like if you're trying to do sort of like more online step planning.
Yeah. So the reference for this is, so we have an xref and uref. The xref just takes the whole robot and just slides it. So xref is just a linear interpolation between the initial state and the goal state. So nothing crazy there. And the uref is just we assume that the torque is 0, and we assume the two forces are just going to directly oppose gravity and suspend this thing up here. Because we know that like this thing's going to be moving around a little bit, but for the most part, it's going to be supporting the weight of the top body the whole time. So we initialize uref with that. So like what we've seen before, like for the quad rotor, is that our reference will be we take the quad rotor and we like maybe just like have it follow a path from like a double integrator or something. And then the next thing we'll do is that we'll say our uref will just be like, the rotor torques or the rotor speeds that are going to like keep the quad rotor in the air basically. And we know that like it's gonna be doing like more aggressive things or whatever. But for the most part, this thing is like really just kind of like hang in the air. So like that's like a general approach to how we create these reference trajectories. Does that answer your question?
Yeah, no, I know, I think it does. Thank you.
Cool. All right, so in that case,